Hello, welcome to this lesson on the F distribution. This lesson includes a brief introduction to the F distribution and then some theory and results related to the F distribution, including F quantiles, connections with other distributions, connections with ratio of two sample variances, and F distributed ratio of quadratic forms, non-central F distribution, and finally R functions for the F distribution. So let us start with the introduction. The F distribution is named after the statistician Ronald Fisher. So F comes from Fisher. The family of F distributions consists of continuous probability distributions indexed by two positive degrees of freedom parameters. They are called the numerator degree of freedom and the denominator degree of freedom. So unlike chi-square and t, which had only one degree of freedom, F distribution has two degrees of freedoms. The notation capital X tilde F subscript ND indicates that the random variable capital X follows an F distribution with numerator degrees of freedom N and the denominator degrees of freedom D. So in the notation, we write down X as F distribution, and then in the subscript, we write down two numbers. The first number is the numerator degrees of freedom. The second number is the denominator degrees of freedom. Usually in practice, these both numbers are integers, positive integers. But theoretically, they don't have to be integers. They can be real numbers, but positive real numbers. This F distribution is widely used for comparing population variances, especially in two normal distributions. And in the analysis of variance, also in regression analysis and other statistical procedures involving ratios of variances. So therefore, F distribution is a very, very useful distribution, and it appears in a lot of situations, especially in statistical inference. Now let us see how an F distribution arises naturally in practice. Suppose you have a chi-square random variable denoted by U, and suppose it has a chi-square N distribution. And also suppose there is another random variable V, which has a chi-square D distribution. And in addition to that, suppose that U and V are independent. Then if you define X to be U divided by the corresponding degrees of freedom divided by V divided by the corresponding degrees of freedom, this quantity is a new random variable. It has some distribution. That distribution is called the F distribution with N numerator degrees of freedom and D denominator degrees of freedom. So in this case, X has an F distribution with N numerator degrees of freedom and D denominator degrees of freedom. We usually denote, in short, this thing as X has a F N D distribution. Now, the order of these two numbers are important because, as I mentioned, the first number must be the numerator degrees of freedom That name comes because that is the degrees of corresponding to the numerator term in this ratio. And D here is the degrees of freedom of the variable in the denominator of this ratio. Right? So F arises as a ratio of two chi-square, independent chi-square random variables. So N numerator degrees of freedom is the degrees of freedom of the variable in the numerator. Denominator degrees of freedom of the F distribution is the degrees of freedom of the variable in the denominator of this ratio. Right. So therefore, FND and FDN are not equal or equivalent in general. Right. So what are the principal properties of the F distribution? The F distribution is defined only for non-negative values. So if some random variable has an F distribution, X must be greater than or equal to 0. The shape of any F distribution is generally positively skewed. Positively skewed. Its shape depends on both the numerator and denominator degrees of freedom, and later on we will see how the shape changes with these degrees of freedoms. An important result for a F distribution is that if X has an F distribution with N and D degrees of freedom, expected value is equal to D divided by D minus 2. So you see that the expected value does not involve the numerator degrees of freedom N. The expected value of the F distribution depends only on the denominator degrees of freedom. And you can see that as D increases, this thing will come close and close to 1. Right? So when an F distribution has a large denominator degrees of freedom, then its expected value is close to 1. Now, how does that expected value not depend on N in this case? It's not that difficult to see that. I'll write down it here. Remember, this X here was defined as U divided by N, U divided by N divided by V divided by D, where U and V are independent, right? U and V are independent. This is how we write down usually independence in when you write down statistical. Now, if you look at the expected value of X, that is equal to expected value of this ratio, but that can be written as expected, because U and V are independent, we can write down like this. This is equal to expected value of U divided by N times expected value of 1 over V divided by D. V divided by D. Right. It is, remember, it is not equal to expected value of U divided by N divided by expected value of V divided by D. That is not correct. But because these two quantities are independent, this can be written as this one. Expected value of U over N times expected value of 1 over V divided by N. Now we know that U has a chi-square distribution with N degrees of freedom. So therefore, expected value of U divided by N is equal to expected value of U divided by N. And I will leave this part here as it is. V divided by D. I will leave that part. I will simplify only this part. And this is equal to expected value of U will be equal to N, because U has a chi-square distribution with N degrees of freedom. And for the chi-square distribution, expected value is equal to N. So N divided by N n divided by n times expected value of 1 over v divided by d. But this one, you can see that n cancels out. So that is why n is not appearing in the expected value of x. And we can show that expected value of 1 over v divided by d, or that is the same as expected value of d divided by v to be this number. If we apply, if we use the uh, definition of the expected value of a 1 over v of a chi-square random variable, we will get this expression. Right. I just wanted to show you why the expected value doesn't depend on n in this case, numerator degrees of freedom. And this is defined, of course, you can see that it has to be d greater than 2, otherwise this quantity can be negative, which is not possible because x is a positive random variable, so its expected value cannot be negative. So for this to be a positive value, d has to be greater than 2. Right? So this expected value, therefore, for a f distribution with denominator degrees of freedom is defined when d is greater than 2. Otherwise, it is not defined. It does not exist. The variance, on the other hand, contains both n and d, and it is a little bit complicated equation that is not very, it's not easy to remember also, but that is the variance of x. Right. Now, I'll show you using our Shiny app how the shape of the density change uh, with the two with the changes of the 2 degrees of freedom. Right. So for that, I will use this Shiny app. So what you see here is actually an F distribution with numerator degrees of freedom 5 and denominator degrees of freedom 10. Right. And remember, I told you that when the denominator degrees of freedom uh, increases, the expected value will be reaching to number 1, value 1. And I have indicated the value 1 here, right? So at this point, for this degrees of freedom, for when d is equal to 10, of course, the mean is equal to 1.25. So it will be somewhere here, mean, right? Now I will keep the numerator degrees of freedom fixed and increase the denominator degrees of freedom, and we'll see what happens to the shape. Right. So when I increase to say denominator degrees of freedom to 20, now the mean is equal to 1.1, which is very close to 1 now. What happened? Again, let me start with 10. So you can see that so earlier, actually what happens here is when I increase this thing, the scale also changes. So it's a little bit difficult to see actually what happens. So let's keep track on this. Here at the moment, when the degrees of freedom 11, here I have 6 as the maximum value of the x-axis. So let's change this, increase this. Right. So you can see now 6 has moved to that side. So that means the distribution is moving to the left. Right. So that means the skewness, all these distributions are positively skewed, but now you can see the skewness is decreasing as the degrees of freedom is increased. Skewness is decreasing. Right. When the denominator degrees of freedom is 100, this is the shape. In this case, the numerator degrees of freedom is 5. Right. So now I will keep my denominator degrees of freedom at this point, and then we will see what happens to the shape when we increase the numerator degrees of freedom. At the moment, it is 5. Right. So when I increase the numerator degrees of freedom, also you can see now it's further reducing the skewness, and now the distribution is becoming more and more normal looking, right? And for example, now it's almost like a normal distribution. Not necessarily a normal, because it may not have the normal properties, like the density doesn't come to uh, zero, very close to zero, as the value becomes -3 or +3, right? This is, I mean, in a standard normal distribution, but otherwise mean -3 standard deviation or mean +3 standard deviation. At those values, the density should be approximately zero for a normal distribution. But in this case, it's not like that. But the shape becomes more and more normal looking as both degrees of freedom are increased. So let me now keep my denominator degrees of freedom at some value like 10. And then starting with some value like 5, I will increase. Again, you can see that the skewness decreases, right? So increase of both degrees of freedom makes the distribution less and less skewed, right? Now we look at F quantiles. Again, like in the chi-square and T distributions, quantiles are very important. But as I mentioned in the other distributions, uh, their notations are different in different books written by different authors, right? So therefore, I introduce three of those notations with a warning that whenever you look at a quantile notation, you have to first find out its definition in that particular research paper or in the book. Also, when you write down some notation, right, for a quantile, you better define it before you use it other places. Otherwise, the reader may not know exactly what you mean by that notation, right? So some books use this notation here. This is the more common notation, I think. Suppose X has an F distribution with, say, numerator degrees of freedom nu1 and denominator degrees of freedom nu2. Here, both are denoted as nu1 and nu2. Nu1 is the numerator one, nu2 is the denominator one. And suppose P is a probability between 0 and 1. And let's consider a value K satisfying this probability statement. Probability X less than or equal to K is equal to P. Then this K is the one that we call the pth quantile of the F distribution with nu1 numerator degrees of freedom and nu2 denominator degrees of freedom. And it is denoted as this notation here, right? F, and then in the subscript, we write down P first, that is the probability, and then the 2 degrees of freedom in order. The first one is the numerator one, second one is the denominator. So that is the common notation for a pth quantile of a F distribution. So for this pth quantile, the probability X less than or equal to that quantile is equal to simple P, right? We can obtain this value when we know the value of P and nu1 and nu2. We can obtain this value numerically using the R function QF. So this is the application. You have to say QF and then within bracket value of P first, and then numerator degrees of freedom as the second argument, and the denominator degrees of freedom as the third argument. So for example, if you put P equal to 0.95 and nu1 equal to 5 and nu2 equal to 10, R gives you value 3.326, rounded to 3 decimal places. So because it is the 0.95th quantile, right? According to this notation, this value here, 3.326, can be denoted as f.95, 5, 10. Right? So according to this notation, that will be the notation for this 3.326. Right? First number is the probability below the quantile. Second number is the numerator degrees of freedom. Third number is the denominator degrees of freedom. Right. And in some books, you will see a different notation for the same value, 3.326. It will be denoted by another different one. In that case, they use this definition for the quantile k, right? So suppose k is a constant satisfying this probability statement where this alpha is a probability. Probability x greater than k is equal to some value alpha. In that case, usually it is called the upper tail critical value of the F distribution with nu1 numerator degrees of freedom and nu2 denominator degrees of freedom. It's called the upper tail critical value. Right? It doesn't have to be a tail, it can be somewhere here also, but it gives you the upper probability, that the probability above the table to be equal to alpha. Probability above the quantile or that critical value to be alpha. Right? So according to that notation, the same value 3.326 will be denoted as f.05, 5, 10, because the area above this thing is 0.05. Area below 3.326 under the curve is 0.95. Area above that is therefore 0.05. And so according to this notation, alpha is the area above the quantile or the critical value. So therefore, that value will be appearing here as the first subscript, f.05 and then 5, 10. Right? So the same value by different authors may be denoted by different notations. Right? And there's another variation of these things. Some authors uh, change the order of these things. Of course, you cannot change the order of nu1 and nu2. They should have the same order. But some people write down alpha after nu1, nu2, after nu2, right? Some other books place the degrees of freedom before the upper tail probability and denote the same upper tail critical value by f nu1, nu2, alpha. So they write down nu1, nu2 first and then alpha at the end. As far as these two notations are concerned, they are not going to be confusing because we know that nu1 and nu2 are in general greater than or equal to 1. Alpha is a number between 0 and 1. Right? So therefore, whenever you have numbers here instead of the notations, for example, uh, two numbers should be the degrees of freedom and the decimal number should be the probability. But this notation and the previous notation can be confusing. Right? So therefore, it's always better to write down your definition of the notation before you use it throughout your research paper or maybe in your thesis, right? Or even in exam answers, right? Right. Now we will look at some relationship between F distribution and some other distributions, relationships or connections, right? Connections with other distributions. Now suppose there is a T distribution with the say d degrees of freedom. Let's denote that random variable by capital T. Then we can prove that T square has a F distribution with numerator degrees of freedom 1 and denominator degrees of freedom D. How do we see this one? This is not that difficult. Remember, we define an F distribution. F distribution arises as the ratio of two independent chi-square random variables. Suppose U has a degrees of freedom n, and has a chi-square distribution with n degrees of freedom. So U divided by n divided by V divided by, say, D, where V has a chi-square D distribution. So U has a chi-square n distribution. V has a chi-square D distribution. In addition to that, U and V are independent. Then under these three conditions, we know that this ratio, if we denote it by, let me call it X, for example, X, then X has a F distribution with n numerator degrees of freedom and D denominator degrees of freedom. But now let us look at, for example, suppose this U is also, you notice that a T random variable T arises as the ratio of Z divided by some, I'll call it W divided by the corresponding degrees of freedom square root. And if Z and W are independent, right? Z has a standard normal and W has a chi-square new distribution, and Z and W are independent, then we get this. If you look at this ratio, this has a T new distribution. T new distribution. Now let's consider this T square. T square is going to be Z square divided by W over nu, right? But remember that when Z is standard normal, Z square is like a U because it has a chi-square distribution with 1 degree of freedom. Z square has a chi-square 1 distribution, and whatever this thing has a chi-square new distribution. So from this one, we should get an F1 new distribution. This ratio should have F1 new distribution when Z and W are independent, right? So that's what is happening here, right? Because when U is equal to Z square, right? That means in a T square, U is the same as this is Z square, right? When you look at T square, we have this kind of one with Z square here, which has a chi-square 1. So the numerator degrees of freedom is 1, right? So that is why this T square has a F1 new distribution, right? Or in this case, if you have V, the second term has D degrees of freedom. If it has a D degrees of freedom here, and if it has D degrees of freedom here, then this will have a chi-square D, and therefore this will have a F1D distribution, right? So I think it's clear to you now why T square has a F1 distribution. Now, some other connections. Suppose X has an F distribution with N and D degrees of freedom, then we can prove easily 1 over X has an F distribution with numerator degrees of freedom D and denominator degrees of freedom N in that case, right? This is also very easy to see. For example, suppose X is equal to, say, some U U divided by N and V divided by D, where U and V are independent chi-square random variables with N and D degrees of freedom respectively, then 1 over X is equal to V divided by D divided by U divided by N. So naturally, then this should have a F distribution with D numerator degrees of freedom and N denominator degrees of freedom. So that's what we have here. And the first number is always the numerator degrees of freedom. Second one is the denominator degrees of freedom. So that's a useful result also. And because of that, we can find out a relationship between the quantiles as well. Right? I'm using the first definition that we discussed earlier as for the quantile. Suppose X has this FND distribution, and in that case, the probability X less than or equal to this quantile will be equal to P. So this will be the Pth quantile of the F distribution with N numerator degrees of freedom and D denominator degrees of freedom. Right. But now this is equal to P. I can write down the same probability statement equivalently like this. That is the same as the probability 1 over X greater than 1 over this quantity. But this is equal to 1 minus the probability 1 over X less than or equal to this quantity. Right. So therefore, from this one, we can get probability 1 over X less than or equal to this quantity is equal to 1 minus P. You can take this to this side. So this is one expression that I need, right? Probability 1 over X less than or equal to this quantity is equal to 1 minus P. On the other hand, 1 over X has a F distribution with D and N degrees of freedom. So therefore, the probability 1 over X less than or equal to this quantity will be equal to 1 minus P. 1 minus P. Here is the 1 minus P. But now we can write down this thing 1 over X less than or equal to F 1 minus P D and N. Right. Is equal to 1 minus P. Right. So these both expressions are giving 1 minus P on the right side. So therefore, the left-hand side should be equal. So in both cases, we are looking at the random variable 1 over X. Right. So therefore, this number here, 1 over FPND, should be the same as F1 minus P dN. Right. So from that, I can get this expression. Right. F P and D is equal to 1 over 1 minus P dN, right? So in this case, D is the numerator degrees of freedom, N is the denominator degrees of freedom. Or you can write down F1 minus P dN is equal to 1 over FPND. This relationship was very, very useful earlier days when we didn't have computers to find out quantiles. And in those days, we were using tables, statistical tables containing F distributions. And because there are so many F distributions changing with N and D, there were tables only for some P values of P for small P values. Right. Actually, those tables contained those critical values rather than quantiles. Right. So if you wanted to get critical values for large P values, you had to use this relationship in that case. Nowadays, we can get any quantile using, for example, R without using this kind of relationships, but it is nice to know these relationships and how they came. Now we will look at the connection with F distribution to the ratio of two sample variances. Right. Suppose you have a random sample x1 up to xm from a normal distribution with mean mu x and variance sigma square x. So this x1 up to xm are IID normal. Suppose you have another random sample y1 up to yn coming from some other normal distribution with mean mu y and some other variance sigma square y, right? In general, the means can be equal, variance can be equal, but here, what important thing is this sample is independent of this sample. Within the sample x1 up to xm are independent. Within this sample yn up to ym n are independent. And between xi and xj, between the two samples, any xi is independent of any yj. Right. Now, using this sample, let's get the sample variance. Let's call it as x square. Using this sample, let's define the sample variance denoted by as y square. And then from previous knowledge that we discussed under the chi-square distribution, we know that when the data are normally distributed, m minus 1 sx square divided by sigma square, corresponding sigma square has a chi-square m minus 1 distribution. And similarly, this quantity has a chi-square n minus 1 distribution. In addition to that, we know that sx square and sy square are independent because they are coming from two independent samples. So if I now apply our F ratio, like this quantity divided by its degrees of freedom divided by this quantity divided by its degrees of freedom. So let me take Q to be m minus 1 times sx square divided by sigma x square divided by its degrees of freedom divided by n minus 1 sy square divided by sigma y square divided by its degrees of freedom. So you can see that these are cancelling out, and therefore Q is equal to this quantity, and that should have F distribution because these two are chi-square and they are independent. So the ratio should be F with the corresponding degrees of freedom. Numerator degrees of freedom should be m minus 1 and denominator degrees of freedom should be n minus 1. So that is a useful result. This quantity has a F distribution. Notice now this quantity contains the random variables involving x1 up to xn and y1 up to yn. And in addition to that, there are parameters in it, unknown constants. But the distribution of that quantity does not contain any parameter. Right? And you already know that this kind of quantity is called a pivotal quantity when the quantity contains the random variables and the parameters, but the distribution doesn't contain any parameter. This type of quantity is called a pivotal quantity. This pivotal quantity is very useful in statistical inference, especially when you want to construct confidence intervals for the ratio between the variances of two independent normal distributions, as well as when you want to test, for example, the equality between the variances of two independent normal distributions. So that will be used later on when we talk about the statistical inference. So this is a very useful result. So up to that point, all the results were involved involving univariate distributions, right? Univariate cases. Right? Now we are going to look at a multivariate extension of this idea, F ratio. Suppose y, vector y, random vector y has a p-variate standard normal distribution. P-variate standard normal distribution with mean vector 0 and variance covariance matrix, identity matrix. And let A and B be symmetric P by P idempotent matrices satisfying A times B equal to 0. Right. And suppose that the trace of M A is equal to N and the trace of B is equal to D, some two values. Then, if you look at this ratio, that should have a F in D distribution. Why is that? Because this Y dash A Y is a quadratic form, and that has a chi-square distribution with n degrees of freedom when A is symmetric P by P idempotent matrix and Y is uh, multivariate standard norm. So we have already learned about that under the multivariate normal distribution. Y dash A Y, that is a quadratic form. That quadratic form has a chi-square n distribution. So what we have done is chi-square random variable divided by its degrees of freedom. Similarly, y dash by should have a chi-square d distribution. And here we have that quantity divided by t. Right. So therefore, this is a single random variable now. Y dash ay is a single random variable. Y dash by is also a single random variable. Right. So we have the ratio and in addition to that, because A times B is equal to 0, when AB is equal to 0, these two quantities are independent. That was also discussed under the multivariate normal distribution and also under the random vectors lessons. Right. So what we have here is a chi-square n random variable divided by its degrees of freedom divided by a chi-square d random variable divided by its degrees of freedom. When the two random variables are independent, it has a F distribution with n and d degrees of freedom. Right. So this is the explanation of that. I have already done it. So I will just keep it few seconds for you to see it. Right. Now we come to almost the end of this lesson. Before that, we will look at the non-central F distribution. Non-central F. Up to now, all the F distributions that we were talking about, therefore, were central F distributions. Usually, we don't call it central F, we just say F distribution. But now, because we are talking about F as non-central F, they should be called non-central. Sorry, they should be called central F. Right. So, how does a non-central F distribution arise? We know a central F distribution arises as the ratio of two independent chi-squares divided by their corresponding degrees of freedom. U has a chi-square n distribution, V has a chi-square d distribution, and both are central chi-squares, and U and V are independent. In that case, this ratio has a central F distribution. But if this U now has a non-central chi-square with n degrees of freedom and non-centrality parameter, say delta, and V has a central chi-square with d degrees of freedom, and if U and V are independent, then this ratio has a distribution. That distribution is called the non-central F distribution with numerator degrees of freedom n and denominator degrees of freedom d and the non-centrality parameter equal to delta. So we denote it as, for example, like this. I have denoted the random variable also by capital F here. That's okay. So that random variable F has F distribution with n numerator degrees of freedom and d denominator degrees of freedom and non-centrality parameter delta. Right. And the central F distribution, of course, can be obtained when delta is equal to 0. So what happens when delta is not equal to 0? In this case, delta has to be a positive value, otherwise, generally it has to be non-negative, right? So if delta is a positive value, then that non-central left distribution is usually used again in power calculations of statistical tests, right? I have mentioned that in the lesson under the lesson for the chi-square and t also, right? So these non-central distributions are very useful in calculating power of test of hypothesis. Now let us look at what happens to the density of a non-central left distribution when we change the value of the non-centrality parameter. For that, I have a Shiny app. So let me use that app now. So here at the beginning, I have only the non-central F distribution with 5 numerator degrees of freedom and 10 denominator degrees of freedom. Right? You can see that it's a positively skewed distribution. Now let me change. In this case, non-central parameter is 0. Now I will increase it, right, little by little. So you can see now you have two curves. The red curve shows the non-central F distribution, non-central F distribution. So you can see that non-central F distribution has a longer tail in this case than the central F distribution. So let's see what happens when we increase, but then the scale will be changing also. So let's keep track on this number 6 here, right? Right. Now you can see what happens to the red curve. The blue curve is fixed. The red curve, you can see that now when we increase the non-centrality parameter, the skewness increases. Earlier, this point was somewhere here 6. Now it has gone up to 10, for example. So you can see the positive skewness increases with the increase of the non-centrality parameter here. Okay, so that is, I think, enough for the moment for the non-centrality F distribution. Now, as the end of this lesson, I show you the R commands commonly used for the F distribution. So they are denoted by they are DF, PF, QF, and RF, giving the probability density, cumulative probability, quantile, and random observations. Right. Uh, Generally, by default, the non-centrality parameter is 0. So if you don't give a value for NCP, then all the values given by these functions are related to the central left distribution. But if you provide the positive value for the NCP, then these functions will be giving the corresponding quantities for that F distribution with numerator degrees of freedom df1, denominator degrees of freedom df2, and with whatever the given non-centrality parameter. So that is the end of this lecture or this lesson, right? That is also the end of chapter 4 of the Demidengos book. So in the next lesson, we will start chapter 5, where we will start some preliminary data analysis in that lesson, right? So that is the end of this lesson.